Okay, gang, welcome to CSC 475. We've got this lecture and one more, and that'll be it for the quarter. Today, what we're going to do is we are going to talk about first order logic. We've been talking about propositional logic. We've talked about reasoning. We've talked about conversion to conjunctive normal form. We've talked about resolution. We're going to recover all of those topics, but now instead of covering them from a propositional logic perspective, we're going to cover them from a first order logic or predicate calculus, predicate logic perspective. I say these things, predicate logic or first order logic, I'm talking about exactly the same thing. They're just synonyms for the same thing. So that is what we're going to be doing today. So let me share my screen and get started here, if I can find my notes. Okay. So first order logic, often abbreviated FOL, as opposed to LOL, is first order logic, sometimes called predicate calculus, sometimes called first order predicate calculus. Sometimes people, if someone is talking about AI and they just say logic or formal logic, they probably mean first order predicate calculus. Basically, first order logic is built around the concept of objects. You can think of these as nouns like people, Mike, baseball, etc., and relations, round, bogus, male, which are taking a single input, right, a single object, like a round baseball would be an example of a relation, which is basically a way of saying baseballs are round. Male, female, those are relations that take in a single object, like a person, or it could be any mammal, right, or male and female. But then there are multi-input relations, like brother of. In my case, Mike is the brother of Ed. So Mike and Ed are the inputs there. Owns. Mike owns Tesla, right? Not the company, sadly. A Tesla, as a particular car. Bigger than. Everyone bigger than Mike. But no, you get the idea there that that you've got relations and you've got objects. Okay. So what's the advantage of this logic? Why are we talking about it? Because it's far more powerful, it's more expressive. You can say things using first order logic that you just simply can't say in propositional logic. So it's a lot more powerful, that's why we study it. However, with power comes certain negatives, certain disadvantages. So on the plus side, there exist proof procedures in which all attempts to prove a particular first order statement is true are guaranteed to halt with a successful proof if in fact the statement is true. Blah, 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 lots of words. What are you saying there, Mike? If I set out to prove that something is true and it really is true, I have to be real careful here. If I set out to prove that something's true and it really is true, as in it really is implied by the true things that you already know, then you will be able to find a proof of that thing being true. So if I go to prove something is true and that thing actually is true and logically follows from other things that I know, then I will be able to find a proof of that thing. However, if you try to prove that something is true when in fact it's actually false, in other words, it conflicts with what is already known, you're not guaranteed to be able to find that in first order logic. In propositional logic, if something conflicted, if something was false, you would be able to prove that, okay? But in first order logic, you lose that. Again, let me try to rephrase it. Remember when you took theory of computing, we talked about the halting problem, right? I assume most of you have had theory of computing. Basically, a program, if you're running a program, it can either halt or it can go into an infinite loop. First order logic is similar. It is only semi-decidable. If you try to prove something that is in fact true, if you try to prove something's true that is in fact true and follows from the statements you already know to be true, then you will find a proof. The process will halt. However, if you attempt to prove that something is true when in fact it isn't true, you might prove that, or you might get stuck in an endless loop. So a statement may discover that something, a procedure may discover that a statement that you're introducing is false, or it may run forever. So logic, first order logic, is semi-decidable, just like regular programs, just like Turing machines. You can't be sure that you'll actually get an answer, even if an answer exists. I said that propositional logic is fully decidable. Now, why is that the case? Well, even though we've used resolution and we used chaining of implication and modus ponens and modus tollens, we used all those reasoning rules, but really anything that you state, any group of statements that you make in propositional logic can be represented by a truth table. So if I've got P propositions, a truth table with 2 to the P rows in it will capture absolutely everything about what was said there. So you could answer any question about, well, what if P1 was true and P3 was false and P2 was true? And, if you could answer any question by just looking up the appropriate row or rows in the truth table. And while 2 to the P is very large, assuming that P isn't, 0 or 1 or 2, it's finite. First order logic deals with infinities in a sense, so you can't write down every possibility. And so first order logic is not fully decidable like propositional logic. Did that make sense? Any questions about that? Bottom line, propositional logic is simpler. You can say fewer things, but because it's simpler, it's fully decidable. A properly written proof system would never get stuck in an infinite loop. With a first order logic system, it's more expressible. You can say things that are not possible to be said in propositional logic, but what you're giving up is that it's semi-decidable. Okay? Does that make sense? Yes, no, maybe in the chat? Okay. Now, here's a little thing that often isn't said in this class, but should be said, and that is that there is a workaround to the fact that a logic is semi-decidable. If I've got a statement and I don't know whether it's true or whether it's false, and I want to be able to get an answer, and I want to make sure that I don't get stuck in an infinite loop, all you need to do is try to prove that it's true in one instance of the system and prove that it's false in another instance of the same system. And if you run those in parallel, one of them is guaranteed to eventually halt. And then you just terminate the other process that may or may not be in an infinite loop. Does that make sense? So when I start out on a proof and I try to prove something, it could get stuck in an infinite loop, but only if the thing that I'm trying to prove is actually false. And if I don't know it first, well, let's try to prove it true and let's try to prove it false. Both of those may halt. One of them may get stuck, but since there's only two outcomes, either true or false, I can just run both of them, and one of them will be guaranteed to halt, at least one. And when that happens, I can terminate the other process, and everybody's happy. That's not usually said, but I figured I'd go ahead and say it because it is actually, from an implementation point of view, extremely important, obviously. Okay. So we're going to have a new story. This is going to be a story that's going to be in first order logic. I'm pulling this story from the textbook that I learned artificial intelligence from. First I learned it on my own, and then I took a class in it in graduate school at ULL, and we used that textbook, and then I later used that textbook in teaching this course many moons ago. And this is the textbook that I made fun of that had one paragraph on neural networks. But it was a very good textbook, and it was the standard textbook for many years in AI. Let's read through the story, and then we'll start talking about it. Marcus was a man. Marcus was Pompeian, meaning he was from Pompeii. All Pompeians were Romans because Pompeii was a city in Rome, so if you were from Pompeii, then you were Roman. We're leaving out the whole idea that there were a lot of people who lived in Rome that weren't citizens of Rome, they were slaves. But all Pompeians were Romans. Caesar was a ruler. All Romans were either loyal to Caesar or they hated him. Everyone is loyal to someone. People only try to assassinate rulers they are not loyal to. Marcus tried to assassinate Caesar. Okay. This is, a little bit of the story of Julius Caesar, and so we can reason about this story. But if we want to reason about it, the first thing we need to do is we need to convert it into logic, first order logic. And the first thing we come to is Marcus was a man. That's normally encoded by something like man, open parentheses, Marcus, close parentheses. Man is a relation. Marcus is an object. It's a thing. And basically what you're saying there is that Marcus is a man. Okay? That is generally how you encode a statement like Marcus was a man. Now remember, I have said that when you translate English into logic, you lose shades of meaning. We are losing some shades of meaning here. The first thing, which may or may not be important to the story, we don't really know. But as a human who's read the story and as a teacher who knows what I'm going to do with this, I know that the fact that the sentences are written in past tense makes no difference. So we are losing the idea that Marcus was a man is written in the past tense. In fact, because it's stated in the past tense, a human would probably come away with the idea that Marcus is no longer a man, probably because Marcus is dead. That's usually when we speak about someone in the past tense, and using a general statement like that. If I were to say, my father was a man, or if I were to say, my brother is a man, you can generally, human to human, know that I'm saying that my father's no longer alive, but my brother is alive. But again, all those shades of meaning are going away here. You're just recording the fact that Marcus is an instance of the relation man. Okay? But there's always loss. And that's the problem. That's the root problem as to why logic didn't end up, logic-based systems didn't end up solving artificial general intelligence, because the translation problem from English, which is gooey and incomplete and inconsistent and filled with tons and tons of shades of meaning, doesn't, there's no algorithm for converting without loss to logic. So anyway, Marcus is a man. Marcus was Pompeian. Okay, so the same sort of thing. Pompeian, open parenthesis, Marcus, close parenthesis. Marcus is an instance of the group Pompeian. So again, we're losing the past tense, but we seem to have captured the main point. Now notice, you could not, in propositional logic, I could not have written statements 1 and 2, because I could say Marcus man as just a proposition, but that wouldn't really make any kind of linkage between the concept of man and the instance Marcus, right? And same thing with Pompeian. Saying that Marcus is Pompeian, the way we're doing it here in first order logic is you're indicating that Marcus is an instance or of Pompeian is what you're doing here. Now, how about statement 3? All Pompeians were Roman. All Pompeians were Roman. That's English equivalent to if someone is Pompeian, then that someone is Roman. Would you agree? If I say all Pompeians were Romans, if someone is a Pompeian, then that same someone is a Roman. Okay. That's a good point, Zach, about it being object-oriented. It is, in very much. A lot of object-oriented concepts derive from AI research. So statement 3. This is one that's got a symbol that we've never seen before, an upside down A. When you see an upside down A, that means for all. That's how it's read, for all. For all X, Pompeian X implies Roman X. For all X, if X is Pompeian, then X is also Roman. That kind of captures the idea that all Pompeians were Roman. Now, you always lose shades of meaning. If I say all Pompeians were Roman, and you know what a Pompeian is, and you know what a Roman is, you know that that statement is excluding pretty much cats and dogs, right? We mean people, so if we look at statement 3 is saying anything that meets the definition of Pompeian, which I misspelled. Anything that meets the definition of Pompeian, that same thing will also be Roman. Okay, so I'm leaving out the idea that X is also a human. That's fine for our purposes. How about Caesar was a ruler? Well, similar thing. Caesar probably means Julius Caesar, a particular person, although later on Caesar came to mean was a title for leader, like president or grand poobah or whatever. It was a title, right? But here we probably mean that Julius Caesar was a ruler. That's what we probably mean here. But anyway, Caesar is an instance of the class, if you want to say it that way, ruler. Number 5, all Romans were either loyal to Caesar or hated him. Now, this is a little bit more complicated, but basically you're saying something like, if X is Roman, then either X is loyal to Caesar or X hates Caesar. Okay? And that's what we're saying here in Rule 5. For all X, Roman X implies X is loyal to Caesar or X hates Caesar. You're either loyal to Caesar or you hate Caesar if you're Roman. There's no in between there. Now, there's another problem with this translation that's even more critical, and that is that if we look at the English for Statement 5, all Romans were either loyal to Caesar or hated him. In the logic, I encoded that using this symbol, right? And what is this symbol? It's the symbol for or, but if you go back to the truth table for or, it's defined as an inclusive or, either or both. But I think you could make an ironclad argument that the person who wrote this sentence meant an exclusive or, either loyal to Caesar or hated him, but not both. You're normally not loyal to someone you hate. Okay, so you can either be loyal to Caesar or you can hate him, but probably not both. So one could argue that a better implementation of a better encoding of that idea would be, for all X, Roman X implies X is loyal to Caesar or X hates Caesar, and not that X is loyal to Caesar and X hates Caesar. So I explicitly put the but not both or and not both here, which you need to do if you really wanted to, if it were important to the story and what we were going to do, that was an exclusive or and not an inclusive or. Depending on what you were wanting to do, this might be critical. But we're going to stick with the simpler one because I'm the prof and I know that what we're going to do with this, that this will be good enough. So not only did we lose past tense here, we also lost the meaning that this or is almost certainly exclusive, not inclusive, but I've encoded it using inclusive. These are the kinds of calls you have to make when you're converting from English to logic. And there's no algorithm for it because there's no exact right answer. It depends on what you're trying to do with it. It's almost in some ways like when we were talking about the farmer wolf goat cabbage problem and we didn't model the boat as a location. Why didn't we? Because you didn't really need to, even though if you tell someone the story, you're talking about the left bank and the right bank of the river, and you're talking about the river and you're talking about the boat. So why don't you model the river and why don't you model the boat? Well, because you don't need to. It's not a satisfying answer at all. Okay, so number 6, everyone is loyal to someone. Everyone is loyal to someone. Okay, what does that mean? It probably means for all X, there exists a Y. Oh, here's another new symbol, a backwards E. If you got an upside down A and a backwards E. The upside down A means for all, the backwards E means there exists. So for all X, there exists a Y where X is loyal to Y. Everyone is loyal to someone. Okay? Now, this logic almost certainly reflects what was meant by that statement, everyone is loyal to someone. But this is a vague sentence. Because are we saying that every person has some other person that they're loyal to, where the person they're loyal to can differ from person to person, or are we saying that everyone is loyal to some one particular person or thing? So like in ancient Rome, it would probably be true that everyone was loyal to Zeus, or maybe everyone worships someone. All right. Well, that someone is there. Everybody in ancient Rome was loyal to their god was Zeus. So that's different. That's saying that no matter who you are, there's this one entity that all of those people are loyal to. That would need a different encoding than saying everybody is loyal to someone, but the someone that Mike is loyal to may be different than the someone that Haley is loyal to, for example. So, so what are some of the problems? Again, X and Y, the way I've written this here, is not limited to people. They can be any objects. So, you know, for all X, maybe Mike's frying pan is an X that exists in this world. Okay. Clearly, Mike's frying pan isn't loyal to anyone. Mike might be loyal to his frying pan. You know, I have a favorite frying pan, but so that's one problem. So maybe we should limit this to where X's are peoples, right? If you wanted to do that, you might do something like this. For all X, there exists a Y where X is a person and Y is a person, which implies that in that case where X is a person and Y is a person, X is loyal to Y. But this also would introduce problems because I'm using person here, and of course I never use, well, I used people one time in 7. We'll have to look at that. But mainly I'm using man instead of person, so that could cause a problem. But assuming I solved that, something like this might be closer to everyone is loyal to someone, because when you say everyone, you don't mean every object, you mean every person. So okay. If we did use person, we would have to introduce statements like all men are people and all rulers are people. If we did that, then we could talk about person here and everything would be fine. And so where does this stop? Because like I say here, notice we're quickly getting into the common sense knowledge problem that we've talked about. Everybody knows that men are people. Everybody knows that rulers are people. Everybody knows that when I said everyone is loyal to someone, I'm talking about people, even though I didn't say it. Well, you can't have all of these implied things that are true in a logic system, or your system's going to have holes in it. And when you try to prove common reasonable things, you're going to find that the proofs are going to run into holes and get stuck because they miss. Because they're missing, particular critical pieces of information, so they get stuck. And the second thing is what we were just talking about a moment ago. Assuming we're talking only about people, do we mean that for each person there exists someone he or she is loyal to, possibly a different someone for each person, which is how we coded it. So, Ahmed is loyal to Mohammed and Chen is loyal to Buddha, would fit with statement 6 the way we have it coded. But if we mean there's a single individual, like I was saying in ancient Rome, actually in ancient Greece it would be Zeus, right? In Rome it would be Jupiter, right? Because the Romans just stole the Greek god Zeus and gave him a new name. But everyone is loyal to Zeus. You're saying something different. You're not saying for all X there exists a Y. You're saying there exists a Y for all X. The order of these things matters hugely. If I'm saying for all X there exists a Y where X is loyal to Y, that's allowing the Y is dependent on the X because it comes after the X in our left to right reading. So the Y is actually dependent on the X. Which Y you choose is dependent on which X you choose. If I reverse the order, I'm saying the Y, right, influences the X. So X loyal to Y in this case is saying that, that everyone is loyal to this particular Y. Does that make sense? So this would be something like in a society where everyone is loyal to a particular individual. This is the kind of expression for that. And then I make a statement here that's actually important. Even if we were talking about something like this, right? Everyone is loyal to someone, and we need some particular one. Everybody could still be loyal to, say, both Zeus and Apollo. So you could, just because I'm saying everyone is loyal to someone, that doesn't mean that there's only one Y that could substitute here. You could substitute in the case that I'm talking about here, the Y might be Zeus, and then in another instance, the Y might be Apollo. They might both be true in the same world, where everybody is loyal to both Zeus and Apollo. Does that make sense? Yeah, okay. So hopefully you're beginning to see that, yeah, these quantifiers and the ability to have variables and the ability to have these relations is giving me a lot more power. Yet at the same time, you should be saying, oh, everything I've learned about implication and or and not and all of those things carry over. That's what I meant when we said that this would be pretty easy, because we could talk about all, 80% of stuff with propositional logic, and then I could introduce the differences, here in a follow-on lecture. People only try to assassinate rulers they are not loyal to. This one is difficult, but you have to make decisions. So, for all X, for all Y. X is a person and Y is a ruler, and X tries to assassinate Y. If these three things hold, if X is any person, if Y is any ruler, and if that person tried to assassinate that ruler, then that implies that that person was not loyal to that ruler. That's pretty close to what we're saying here, I think. People only try to assassinate rulers they're not loyal to. So if X is a person and Y is a ruler, and X tries to assassinate Y, that means that X is not loyal to Y. That's what we've coded it as in statement 7. Again, we're using people now. So I'm introducing person as a predicate. I didn't say X was a man because of the way the statement was written. That's obviously going to cause us problems when we try to reason about this. So there's a hole. I'm pointing out here that I'm aware that there's a hole in my representation that you will discover if you try to start using these sentences to reason. Another potential problem, which will turn out not to be a problem in this case, is try assassinate. That's a big glom of stuff that I just put a lot of stuff in and glommed it together. So what does try assassinate actually mean? Well, is that good enough? It's good enough for this particular scenario, so we'll leave it like that. And then finally, the last statement says, if you don't go past it, Mike, the last statement says, number 8, Marcus tried to assassinate Caesar. Marcus try assassinate Caesar. Okay. So, how could we use these rules? Well, before I get into proof by contradiction or resolution and conversion to conjunctive normal form and all of that, let's just see if we can't, simply use essentially modus ponens, where we take if I ask, prove Marcus is not loyal to Caesar. Okay. Prove Marcus is not loyal to Caesar. So if I look at all of my statements, the only one that that concludes, not loyal to, well, we've got 6 that talks about, we've got 5 that talks about concluding loyal to, we've got 6 that deals with loyal to, and we've got 7 that deals with, that can conclude not loyal to. So if I say prove that Marcus is not loyal to Caesar, there are a couple of places that I might have tried to start out. Like I said, I might have tried to start out with 6, but we'll use 7, because basically 7 is an if statement that I want to prove its conclusion is true. The conclusion being not loyal to. And I also, you notice I want to prove Marcus is not loyal to Caesar. So one of the first things you do with first order logic is you can try putting in individuals for the particular variables that are mentioned in the that are mentioned in the logical statement. So if I'm talking about statement 7, I can be, I can reason. Statement 7 deals with, all X and all Y. So I could try, Marcus and Caesar. I could try other things, but I could try Marcus and Caesar. And so, because Marcus is a person and Caesar is a ruler. So if I tried to prove that Marcus was not loyal to Caesar, one way I could do it is I could just use statement 7, which is an if statement, and I could try to use modus ponens. Basically, modus ponens says, you give me an if statement that's true. If the premise is also true, then the conclusion will be true. Well, statement 7 ends in the conclusion I want, not loyal to. X is not loyal to Y. So if I plug in Marcus for X and Caesar for Y, I would get something like person Marcus and ruler Caesar and try assassinate Marcus Caesar implies not loyal to Marcus Caesar. So it would conclude what I wanted. So basically, could I show, is there a way that I can show that the premise of Rule 7 is true? Well, to do that, I have to establish 3 things. I have to establish that Marcus is a person, and I have to establish that Caesar is a ruler, and I have to establish that Marcus tried to assassinate Caesar. Now, I'm putting these here in red because I haven't yet proved those things, but if I can prove all 3 of them, then I can conclude what I've got here nicely in blue, which is that Marcus is not loyal to Caesar. All I'm doing here is trying to use modus ponens. I have an if statement that's given as true. If I can show that its premise is true, then by modus ponens, the conclusion must be true. The conclusion is, of course, this negated thing, not loyal to. So, if I can show that Marcus is a person and Caesar is a ruler and Marcus tried to assassinate Caesar, then I can conclude that Marcus is not loyal to Caesar. So first off, I can knock out that Caesar is a ruler. How can I do that? Rule 4 says that Caesar is a ruler, right? So now I checked this off. It's now green. Okay, so what's left for me to prove to conclude that Marcus is not loyal to Caesar? Well, I need to prove again that Marcus is a person and that Marcus tried to assassinate Caesar. Well, Rule 8 says that Marcus tried to assassinate Caesar. So now I've checked off that Caesar is a ruler and that Marcus tried to assassinate Caesar, so that all that's left for me to prove is that Marcus is a person. So if I can show that Marcus is a person, then given this if statement and that I've showed that these two pieces of the premise are already true, if I can show this part of the premise is true, I will have shown all of the premise is true, and I can conclude not loyalty. Okay. But can I show that Marcus is a person? Well, no, because nothing says that Marcus is a person. So I can fix this by adding a new statement. Originally, I only had 8 statements here. I'm adding a 9th statement that basically says that, what? What does it say? It says that all men are people. So for all X, if X is a man, then you can conclude that X is a person. Every man is a person. Okay? Now that we have Rule 9, right, Rule 9 basically says if I can show man Marcus, that Marcus is a man, then I can conclude that Marcus is a person. And again, if I can conclude that Marcus is a person, I can conclude that Marcus is loyal to Caesar. So Rule 1 states that Marcus is a man. Bam. So by Rule 9, we know that Marcus is a person. And then by Rule 7, now that we can fill this in because we know that Marcus is a person, we can conclude that Marcus is loyal to Caesar. Essentially what I did here was I filled in, I had an if statement, and I was able to show that the conjoined premise was true by proving each of these subparts here. And once I established that all of the subparts of the premise were true, the premise becomes true, so you can conclude the conclusion. Does that make sense? Person is not equal to man. Cody, be careful here. I'm not saying that all people are men. I'm saying that every man is a person. Okay? So this is, every man is a person. That is a true statement. We don't have robotic men yet. So every man is a person. It is also true that every woman is a person. But that would just be another statement that I can add. But if you go back and you look at the story, I never talk about women because this is ancient Rome. Sorry. Bad joke. Bad mic. But my point is I'm not excluding the fact that women are people. Okay? So this is not complete. No system that I try to capture real world knowledge in is ever going to be complete. There are always going to be holes, right? And that's really the whole thing that Doug Lennox tried to do, is he tried to take a logic system and add every one of these friggin' little rules that we're starting to see that we need just to prove things in this simple little thing about Marcus and Caesar here, right? There are, every time you bring up a hole and I plug it, you're going to be able to bring up 2 more holes that I need to plug, right? And the hope was, under the Psych project, that eventually, if you plug enough holes, eventually you will have plugged all of the common sense holes. And then, if you could do that, you could reason about pretty much anything. He tried. Does it work? Well, it never took over the world. Why not? I would argue the biggest problem where logic-based systems like Psych fail is what we were doing here, where we were taking the English and we were converting it. There's no there's no one right way of converting things. They are still trying, that is true. There's no right way of converting statements from English to logic. I'm using my human intuition and my understanding of the problem and my understanding of things that I want to reason about. That's influencing every decision that I'm making here about how I'm doing the encoding. There ain't no algorithm for that. And in my opinion, that's why these systems eventually have so far, Michael, let me be correct. That's why these systems have so far, in my opinion, failed, because it takes human common sense knowledge to be able to do a translation on which you can reason about. And what has happened so far with psych is that it becomes very brittle, because it is so far we've had a team of very bright people. He's got usually about a dozen to several dozen people working on psych at one time that have been working on that for longer than you've been alive, for pretty much my entire adult lifetime, and they haven't succeeded. So will it be possible? Will they or someone else eventually succeed? Maybe. But the fact that we've had brilliant people working on something for pretty much a human lifetime and they haven't been successful shows how difficult the problem is. Would we all agree with that statement? Hopefully. Okay. All right. But my main point is I did not make a mistake here. This is correct. Every man is a person is a true statement. It doesn't capture that every woman is a person, and it's not trying to say that every person is a man. If I tried to say that, if I said for all X, person X implies man X, that would be wrong, because you would be leaving out 51% of the human race at that point. Okay, are we good? I have a few words here that basically say what I did above was legal. I did not use proof by contradiction. All I did was use modus ponens on this if statement. I showed that the premise was true. Because the premise was true and the if statement itself is true, you can conclude the conclusion is true. I have no comment on or understanding of what you're saying there, Michael. And Hannah, yeah, maybe we are all robots. That's an interesting question. Have we tried the Turing test? Now, remember, I think you're asking there, Hannah, have we tried both male and female human judges of the Turing test? I know you're kind of making a joke, but yeah, of course we have. We just showed I showed a video to a class of men and women, and we were all individually judges. Also, the Loebner Prize, they try to balance it with judges of both gender, both sexes, so that they can do that. I don't think there's been any research to show that women are better than men or men are better than women at sussing out fake AIs. Might be interesting to study that, actually, whether or not, like if you took the GPT-3 video that I showed you, that'd be an interesting experiment to do in a psych class, to take like what we just watched there and have humans rate how human the AI is on a scale of 0 to 10, and give it to an intro psych class of men and women, and see whether or not you get any kind of statistical difference there. That would actually be a really interesting experiment to run. Okay. Um, you're in a dream and it's time to wake up. Interesting reference there. Makes me think, of course, of the Matrix, but it also makes me think of when we talk about people potentially being in a simulation. That's no different than if you go back and you look at some ancient Eastern philosophy. There was a thing about, are gods the dreams of men, or is man the dream of gods? It's the same kind of thing when you think that maybe mankind is God's dream. That's just another way of saying that we all live in a simulation, right, for a society that doesn't yet have computers and simulations. So these ideas that seem so new are thousands of years old. We just put them in modern vocabulary now. Okay, y'all have gotten me distracted enough. We need to keep moving forward. So, conversion to conjunctive normal form. So we've done the English, we're down to the sentences, but if we want to do resolution refutation proofs, we need to get these into conjunctive normal form. Except for how we handle universal and existential quantifiers, you've seen all of this before. Basically, you take all of the statements and you connect them together by ands, right? And then each of the individual statements, you have to get into a form where they're all disjunctions, where all of the individual terms are ored together. So we've done all of this, right? So some of them are just, atomic, like Marcus is a man, so there's nothing to change there, and Marcus is Pompeian, and, well, what happens when you have for all x Pompeian, x implies Roman x? For all x not Pompeian or Roman x, not Pompeian x or Roman x. And I'm putting x1 here because the variables between the different statements need to be unique or you're going to screw things up. Just like in programming, I'm using x here and I'm using x here, but if I put these all in one program, and if these are supposed to be different things, I better number them differently or I'm going to screw everything up. So that's where the x1 is coming from. So either not Pompeian x1 or Roman x1, and Caesar's a ruler, so ruler Caesar. So 1, 2, and 3, 1, 2, and 4, I didn't have to do anything. 3 is just P implies Q is the same as not P or Q. Not P or Q. For all x, Roman x implies x is loyal to Caesar or x hates Caesar. Same thing here. Not P or, this is our Q. So not Roman or loyal to Caesar or hate Caesar. And I'm using x2 here rather than x1 because I already used x1 here. And remember, I'm anding all of these into a single statement. So if I didn't use different variables down here, I would be linking 3 and 5, and 3 and 5 aren't linked together in any way. They shouldn't be by their variables. So again, all I did here was, again, not P or Q. Okay? So again, that was the same rule that we used last time. 6 is interesting. What do we do? Okay, Mike, so far, I don't know why, but you seem to be ignoring these universal quantifiers. They're just dropping out in your conjunctive normal form. And they will just drop out. But what do we do about existentially quantified variables? One more word about why the universals are dropping out. Universal quantification is saying for all x, if x is Pompeian, then x is Roman. So it's basically saying any variable that you can find that makes Pompeian, that variable, true, you can conclude Roman with that same variable. And that's really all I'm saying here. If you can find an x1 that makes Pompeian X1 true, right, well then this statement, not Pompeian X1 or Roman X1, will be true. So the universal quantification just means it's trivariable. And if that variable makes this relationship true, then you can conclude this relationship. Okay, so we did that. But what about the existential? The existential is different because I'm not saying that any variable at all will work here, right? In fact, because I'm saying for all x that exists to y, remember we're saying that x is loyal to y, but the y that I choose here is dependent on the x. You know, Mike is loyal to Elon Musk, but, you know, Ed is loyal to Zeus, right? Loyal to different people are loyal to different things. So you can't just say, oh, any old variable will work here for y, because what that variable is going to depend on the x. And the way we do that are with things called Skolem functions. A Skolem function. A Skolem function is a function that you don't need to know how to compute. It's just saying that this is saying that the y that I need, okay, that our x is going to be loyal to, is dependent on our x. So f1 is a Skolem function that essentially computes the individual that x is going to be loyal to. Okay? So I'm getting rid of existential quantifiers by proposing that there be functions that can take as input all of the variables that are universally quantified ahead of that existential quantifier and use those as inputs into a function that returns the result that we need. Are we going to actually compute this thing? No, we're not. But I'm saying that there has to be some mapping from x3 to the individual that x3 is loyal to. And I'm going to call that function right here f1. That's all I'm doing. So basically, the cheat to get rid of existential quantified variables is to propose a function that does the computation that we need. That's the way it works. Okay, for all x, for all y, person x and ruler y and tri-assassinated xy implies not loyal to xy. Again, this is an if statement. P implies Q is the same thing as not P or Q. So not person x and ruler y and tri-assassinate xy implies not loyal to xy. But remember, now I've got a not that I need to drive over these three things that are anded. When you drive a not over a series of ands, the ands flip to ors. So not person or not ruler or not tri-assassinate. So to get to 7, I had to do two things. I had to recognize that I need to use P implies Q is the same thing as not P or Q. And I also had to use the fact that I was knotting all of these things. So if you knot these three things, it becomes not person X or not ruler Y or not tri-assassinate XY. So when you drive an or, a not, over a series of ands, each of the terms get negated and the ands flip over to ors. We talked about this last time if you go back and you look at your notes. Okay? And then tri-assassinate, Marcus Caesar. There's nothing you need to change there. And man X implies person, person X. That's just not man X or person X. And again, this is, why am I using X5? Because, well, the first time I used an X, it was X1. The second time was X2, X3, X4, X5. And every time I used a Y, I incremented it, but I only had one Y, so I had Y1. Does that make sense? over the next little while here, I basically go back through all of that translation that I did here. This is in more detail what I just talked you through. Okay, so if you're still a little fuzzy on it, go and read this. And you really should, regardless of whether you're fuzzy on it or not, you need to go back and you need to read that. You need to understand how I got from here to here, because a very common thing that I will ask on the final is I will give you some statements and I will say convert them to conjunctive normal form. And one or two of the statements might be in propositional logic, but I will have some first order logic statements that will contain some quantified variables, and you will be asked to convert them to conjunctive normal form. Okay? So I'm emphasizing, and you know when Mike emphasizes, that means it's going to be on an exam. Okay. All right. So now that we've converted to conjunctive normal form, and by the way, I'm very glad I haven't goofed up yet, but conjunctive normal form CNF, again, if you had my theory class, you know that we convert things into Chomsky normal form, which is also CNF. So it's so hard when I teach, since I teach both of these classes, not for me to goof up and refer to conjunctive normal form as Chomsky normal form, totally different things in totally different subjects in totally different classes, but they're both CNF, and we both are doing conversions, and so it's sometimes hard for me not to make a mistake. But anyway, we've gotten our statements into conjunctive normal form. Let's say that we wanted to prove that Marcus is loyal to Caesar. I want to prove that Marcus is loyal to Caesar. Now, I will whisper off to the side some spoilers. In reality, and I put reality in quotes because I mean in the reality that we're defining with these 9 statements, Marcus isn't loyal to Caesar. All right. In fact, he tried to assassinate him. So, so this proof has got to fail. Now, I'm whispering this to you as spoilers. You normally wouldn't know whether the thing is going to succeed or fail, right? You just want to prove, hey, I think maybe Marcus is loyal to Caesar. Let me see if I can prove that. So again, since this is a proof by contradiction or refutation proof, I assume the opposite. I assume that Marcus is not loyal to Caesar, and I look for a conflict. You do things exactly the way I showed you last time. You take 2 separate clauses where something is negated in one of them and not negated in the other one. You combine them and you cancel out the negated terms. Now, the only new thing you're doing is you're mapping objects to variables. So if I know that Marcus, if I believe that Marcus is not loyal to Caesar, I have a general rule to talk about Romans loyal to and hate, right? And have a variable in it, x2. I bind x2 to Marcus so I can use this thing here. If I use this and I bind x2 to Marcus, after merging and canceling, I'm left with either Marcus is not Roman or Marcus hates Caesar. Okay, well, nothing says that Marcus is Roman directly, but we know that all Pompeians are Romans, not Pompeian X or Roman X. And so if I bind Marcus to X1, right, I can merge these things, and I end up with the Roman and the not Roman canceling, and I end up that either Marcus hates Caesar or Marcus is not Pompeian. But Rule 2 tells me that Marcus is Pompeian. So since Marcus is Pompeian and Marcus is not Pompeian, when I merge these, I get that Marcus hates Caesar. At this point, you run aground because there's no way to disprove that Marcus hates Caesar. And remember, this is a refutation proof. We're trying to cancel things until we get to a contradiction, which is the empty clause. Well, newsflash, Marcus really does hate Caesar, so you're not going to be able to make any further progress to disprove that Marcus hates Caesar. So this is an example of a refutation proof that terminates when you gave it a false thing and asked it to prove it. Sometimes it grinds to a certain point and there's nothing left for it to try, and it says, I give up. Now, when it gives up, it's very important that you understand that giving up doesn't mean that we've proven anything. In fact, giving up just means I gave up. I don't know whether Marcus is loyal to Caesar or Marcus is not loyal to Caesar. All I know is I tried to prove that Marcus was not loyal to Caesar. Sorry, I tried to prove that Marcus was loyal to Caesar, and I hit a brick wall, and I terminated. I failed. Sometimes in some languages, in some implementations, like in Prolog, failure implies negation. So basically, if I try to prove something and I fail to prove it, I'll just accept the opposite of it. That's not logically valid to do that, but some languages implement that. Again, it's basically a really bad assumption to make, but some languages make that assumption. But essentially, using the rules of logic, we can conclude nothing at this point. Okay? So, can you give me one, Mike, where I actually succeed in proving something? Here's a successful resolution refutation proof. Let me try to prove that Marcus hates Caesar. And that might be a reasonable thing to do because I ended up here trying to disprove that Marcus hated Caesar, and I ran aground on this. I couldn't disprove that Marcus hated Caesar. So why don't I try to actually prove that Marcus hates Caesar? So let me say that again very slowly. When I tried to prove that Marcus was loyal to Caesar, which again isn't true, I tried to prove it, I ended up with Marcus hates Caesar. And because it's the refutation proof, I was trying to show that this was not true, that Marcus really didn't hate Caesar. But I wasn't able to do that. The algorithm stopped. So let me try the opposite now. Let me try to prove that Marcus does in fact hate Caesar, and let's see what happens here, okay? So if I want to prove that Marcus hates Caesar, I assume that Marcus does not hate Caesar, and I try to see if that causes a contradiction. And it does. Marcus does not hate Caesar. That goes with statement 5, where you have X2 hates Caesar, so Marcus is bound to X2. So now either Marcus is not Roman or Marcus is loyal to Caesar, but we know that that Pompeians are Roman, so the not Roman and the Roman cancel. So now either Marcus is not Pompeian or Marcus is loyal to Caesar. I know that Marcus is actually Pompeian from Rule 2. So now then Marcus is loyal to Caesar. I'm trying to disprove that. So I'm trying to disprove that Marcus is loyal to Caesar, which is the opposite of what I was doing here. All right. Here I was trying to prove that Marcus was loyal to Caesar. Trying to show that Marcus hates Caesar has given me to the point of trying to disprove that Marcus is loyal to Caesar. And if you look, you can merge here the loyal to and the not loyal to, Marcus and Caesar being bound. So Marcus is not a person, or Caesar's not a ruler, or Marcus didn't try to assassinate him. You can merge this with 9 here. That gets rid of the thing that we're talking about, man and person here. So now either Marcus is not a man, or Caesar's not a ruler, or Marcus didn't try to assassinate Caesar, but Marcus is a man. So either Caesar's not a ruler, or Marcus didn't try to assassinate Caesar, but Caesar is a ruler. So Marcus did not try to assassinate Caesar, but Marcus did try to assassinate Caesar by 8, which leads to a contradiction, which means that, yes, Marcus hates Caesar. Why? Because if I assume the opposite, that Marcus does not hate Caesar, I get a contradiction. Same old resolution refutation proof that we did last time. You need to practice on some of these. You've got the rules. You've got the conversions to Chomsky. I did it there. To conjunctive normal form. You need to practice on these. There will definitely be at least one resolution refutation proof that I ask you to do. It may be in predicate calculus, first order logic. It may be in propositional logic. I may have one of each or several of each, but you will be expected to do a resolution refutation proof. Make sure you understand it. Sometimes resolution refutation proofs can get stuck in infinite loops. We talked about that. Let me show you an example. Let's expand our little story yet again by adding 2 more rules about persecution. If you persecute somebody, they're going to hate you, right? If I'm really mean to someone and I torture them, I persecute them, they're going to hate me. If you hate someone, though, you tend to persecute them. People you don't like, you tend to be mean to. So statement 10 is saying that if you persecute somebody, then they're going to hate you. Where 11 says that if you hate somebody, then you're going to persecute them. Well, just a little bit of thinking about it, and I convert these right here through logic and to conjunctive normal form. If you think about it, those 2 things will cause you problems. Because now let's say I'm in the middle of something where I'm trying to disprove that Marcus hates Caesar. Well, I can bind Marcus to X7 and Caesar to Y3 in the statement that either X7 doesn't hate Y3 or Y3 persecutes X7. You do that and the hates cancel with the not hate and you end up with Caesar persecutes Marcus. But then 10 says that if X6 does not, either X6 does not persecute Y2 or Y2 hates X6, you do the substitutions and you get back to Marcus hates Caesar. And you see the dot, dot, dot above and the dot, dot, dot below? Because what are we stuck in? We're stuck in an infinite loop where I can disprove that Marcus hates Caesar if I can disprove that Caesar hates Marcus, which I can disprove if I can prove that Marcus hates Caesar, which I can disprove if I can show that Caesar persecutes Marcus, which I can disprove if I can show that Marcus hates Caesar, which I can and at that point on the old classic Star Trek, the computer would blow up. Okay. The last 5 minutes, I think you should read through this carefully. It's only totally a page. What do I do here? I take a complicated sentence. All Romans who know Marcus either hate Caesar or think that anyone who hates someone is crazy, which roughly translates into logic as for all X, Roman X, and X knows Marcus, implies that X hates Caesar, or for all Y, there exists some Z where Y hates Z implies that X thinks that Y is crazy. All Romans who know Marcus, for all X, Roman X, and X knows Marcus, all Romans who know Marcus either hate Caesar or think that anyone who hates someone is crazy. So if you're a Roman and you know Marcus, if X is a Roman and X knows Marcus, then that means either X hates Caesar or this thing about thinking crazy. What does this thing about thinking crazy mean? X is the Roman, right, who knows Marcus. He or she either hates Caesar or for all Y, there exists a Z where Y hates Z. So this is basically saying someone, actually it's saying some entity, could be a desktop, some entity hates Z. There is some Z that exists that Y hates. And because of that, X, the Roman who knows Marcus, thinks that Y, the individual doing the hating, is crazy. Okay? I want you to think about that, and then I want you to go through these steps. I'm going to go back through them on Tuesday at the beginning of lecture, but this is, if you can get through this and you can understand this, you'll be able to translate anything that I'll throw at you to conjunctive normal form, okay? And you'll need to be able to do that because, you know, you don't have, you know, I could give you guys anything. I'm likely not to give you anything as hard as the one that I just showed there, but if you can work through that and you can understand that, then you should be able to get through anything that I give you on the exam. Okay, questions. One other thing, your programming assignment is due at 9 a.m. on Monday. The last time to ask me questions about it is in my office hours on Friday, which is tomorrow. I will be there from 10:30 till noon. And I'll be happy to answer questions. Secondly, if you haven't done so already, please go on Moodle. Please look under assignments. There is now a link to the sign-up sheet for my meetings on Monday and Tuesday. You need to sign up on that sign-up sheet, okay? Please don't wait until Monday. I need you to go ahead and get that taken care of today, okay? If you're a graduating senior, I think I sent an email to all my graduating seniors, but if you're a graduating senior, you need to sign up for Monday because I have to come up with a grade estimate for you and turn it in during class time on Tuesday. So I've got to get it in. Really, I got to get it in on Monday night because all Tuesday morning I'm going to be doing meetings. Okay? And I just lost my video. But anyway, you need to do the sign-up sheet. Okay. That's hopefully my video comes back, but if not, that's still okay. Are there any questions? Since I can't see the screen, you'll have to ask them verbally. Are there any questions? Can anybody hear me? Will someone
Yeah,
say
we can
yes?
hear you.
Okay, good. All right. If there aren't any questions, that's it for me. You guys have a very, very good weekend. Work on that program, and I'll see y'all either on Monday or Tuesday for our meetings, okay? All right. Take care. Bye-bye.